This is a problem where we have a reactor system with a recycle and a purge, and we want to do the material balances to solve for the flow rates at the various locations. We're given the conditions of the feed, which is hydrogen, nitrogen, and methane. So the hydrogen and nitrogen are going to react to form ammonia. In the separator, the ammonia is going to be completely removed and only ammonia. And then the hydrogen, nitrogen, and methane are recycled. But in order to prevent buildup of methane in the system, since it doesn't react, we have to have a purge where we remove some methane as well as some hydrogen and nitrogen. So we have the three flow rates here. We don't know these three flow rates, so there's three here, and I'll use the notation just FH for hydrogen, Fn, and so the 2 now represents the location 2, and then for methane, Fm2. Three unknowns there. There are three here. There's one here because it's only ammonia. There's three here. There's three here. And there's three here. So if we add these up, we have a total of 17 unknowns. Since we have 17 unknowns, we have to have 17 equations. Flow rate of ammonia indicated by NH at 0.4. So let's look at what these equations are. So let's look at the mixing point. And there the mass balance would be flow rate of hydrogen at 1 plus flow rate of hydrogen at 7 equals the flow rate of hydrogen at 2. Now, equivalent equations for the other components. Let me pause and write those down. So let's look now at the flow rate around the reactor. The flow rate of ammonia at location 3 is going to be flow rate of nitrogen at 2 times the fraction converted times 2 for the stoichiometry, since there's 2 nitrogens in N2 and 1 nitrogen in ammonia. The flow rate of methane at 3 is the flow rate of methane at 2, since it doesn't react. The flow rate of hydrogen at 3 is going to be flow rate of hydrogen at 2 times the fraction that did not react, and then likewise for nitrogen. Now for the separator, the flow rate of ammonia at 4 is the flow rate of ammonia at 3, since we remove all of the ammonia. And then the other components, flow rate of nitrogen at 5 is equal to flow rate of nitrogen at 3, and likewise for hydrogen and methane. And so finally we have the balances around the splitting point, and I'll use the notation for, I'll just use the word purge to indicate fraction of stream 5 that ends up in stream 6. So let me pause. The fraction is purge times the flow rate of 5 is flow rate of 6. And we have the equivalent equations for nitrogen and methane. And then finally we have the flow rate of hydrogen at 7 is equal to the flow rate of hydrogen at 5 times 1 minus the fraction that's the purge. And likewise the two equations for nitrogen and ammonia. 17 equations, 17 unknowns. I'm going to solve this in a spreadsheet using Excel solver, and these are linear equations, so it works quite well. We know x is given, so in that equation x is 0.20 and purge is also given in the problem statement, as well as the values of these three flow rates. And so let's look at the solution from Excel. So a separate screencast shows how to use this spreadsheet and shows how we got these results using solver. You know, some checks, of course, is the flow rate of methane coming in equals flow rate of methane leaving. And if we do overall balances on, say, nitrogen atoms and hydrogen atoms, those equations are also satisfied. We did not use the overall balances in the calculation because those equations would be redundant. We can get them by combining the equations we wrote down. So you can see we're losing some of our feed, some of our hydrogen, some of our nitrogen in order to be able to run this a steady state. And you see we're recirculating a significant flow rate of methane through the reactor in order to not lose too much of the hydrogen and nitrogen.